Sounds good. All right.
We need to record. He's already.
Well, he's down now, and
What is it? Why
Okay.
is this happening? Can you hear me? Why is it?
Muted.
I am. Can anybody hear me?
I hear someone talking. All right, let's try this again. My cat has departed, so maybe she won't step on anything and break it either. All right, so now I'm going to try doing a little bit of storytelling with visuals. So let's restart our TARDIS and travel back to 2.6 million years ago again. And so 50 light years away, we have a massive star that ends its life quite violently. And in the expanding degree, we have tiny grains of dust forming. And that dust contains a radioactive isotope of iron that millions of years later, oceanographers find in lumps of manganese minerals on the seafloor of Earth. And then in 2019, astronomers find a neutron star that may be associated with the death of that massive star. Skip forward to the year 185, and Chinese astronomers see a new star in the southern sky that's brighter than Venus, which fades away over the next few months. And then 18 centuries later, astronomers find this lovely nebula in the same spot. A little bit further forward to 1054, and on July 4th, astronomers in China, Japan, the Arabic world, and even Chaco Canyon in New Mexico note the appearance of a new star in the sky that is visible in daylight for 3 weeks and at night for almost 2 years. And then in 1758, Charles Messier catalogs this as the first entry in his catalog of things that are not the comet you are looking for. And almost up to the present day, we get to 1987. And on February 24th, an astronomer in New Zealand noticed a bright new object in the Milky Way's companion galaxy, the Large Magellanic Cloud. And this was an interesting event because when you go back and look at pictures of the same area from before, there is a star right there at the same spot. This is the first one of these events since the closest one of these events since 1680, and the first one in the era of modern astronomy. So we have a tremendous amount of information about this. Observations all the way from the highest energy gamma rays to radio waves and everything in between. We've even seen neutrinos from this object, which are wee subatomic particles that almost don't interact with normal matter at all. You've probably had about 100 billion of them pass through you in the course of this sentence. We discovered 11 of them from this event, which, given how hard it is to interact, tells you this put out a lot of these neutrinos, which will be important later. This is also the first one in the era of computer simulations. So this is actually a simulation of the event done by my graduate school advisor, Dave Arnett, at the time. So this is one of the first multi-dimensional computer simulations that you will see. And all of these events are supernovae. And the ones that we're going to be interested in tonight are the ones that result from the deaths of massive stars. So just to give us a scale to start with, we all know what 100 watts of energy looks like. The sun is 400 trillion watts. A galaxy like the Milky Way is about 100 billion stars. So 10 with 37 zeros after it, watts. One of these supernovae goes off, and it's as bright as another 100 billion suns. For a very brief time, that supernova is putting out as much light as the rest of this galaxy. And supernovae do another very important thing. In order to talk about that, I want to skip backward again to right after the Big Bang. So in the beginning, there was really not much. The periodic table looked like this. There was about 76% by mass of hydrogen, 24% helium, 1 part in a billion lithium, beryllium, and boron, and everything else was present at less than 1 part in a trillion. If we move forward to when the sun forms, it forms with 72% hydrogen, 27% helium, so a little bit different, not too much. But it's also 1.5% other elements, the most common ones being oxygen, carbon, silicon, iron, nitrogen, and magnesium. So 1.5% doesn't sound like a lot, but it's a factor of 10 billion more than the universe started out with, of all these elements. So if we look at our full periodic table here, all of this stuff below these first few are brand new since the universe formed. We did not start out with these. And since I'll be talking about how you make these elements, just want to note that nuclei are made up of protons. That defines what element you have. And neutrons with no electrical charge. That defines which isotope of an element you have. And of course, they all have electrons happily swirling around them. And each element has a variety of different forms called isotopes with different numbers of neutrons, some of which are stable, some of which radioactively decay over time. 92 or so of these elements occur naturally in the Earth's crust. And there are about 7,000 different isotopes that are either stable or that we can measure in the lab. So there is a huge diversity of things represented by this one page of diagram. And this is not just an abstract thing. Having all of these heavy elements that we didn't start out with is kind of essential to our everyday lives. This part of the periodic table is where you get the things that life is made out of. Move up a little bit and you get the major rock forming elements. And then the things that allow us to have a technological civilization. And the shiny elements that arguably keep us from having a more advanced technological civilization. So question is, how do we get from hydrogen, which won't even do this without some oxygen, to rocks and solid useful stuff? Answer, of course, is stars. And in order to understand why that's the case, we need to ask a very, very basic question. And that is, why do stars shine? Well, first of all, they're very large. They are thousands to millions of times as massive as Earth. And if you have a problem getting out of bed in the morning, imagine how that star feels. Gravity is a huge force in its life, and it's going to want to make that star collapse. But the star is made of a plasma that heats up when you compress it. And when you heat up that material, the pressure goes up, which causes it to expand. And that balance is called hydrostatic equilibrium. So the star is not going to collapse. If you squish it, heats up, pressure goes up, so it's nice and stable. Problem is that hot gas emits energy. Just like the filament in that light bulb we saw, it glows. So the star loses energy out into space, shining. And as the star cools off, the pressure is going to decrease and gravity is going to win unless you have an energy source. So what is that energy source? Well, work from our Center for Meteorite Studies at ASU tells us that the oldest solid material in the solar system is 4.5679 billion years old, plus or minus about 200,000. And I just love the fact that we have that incredible precision on something that's old, that is that old. So the sun is 4.5 billion years old. Can you power that with chemical burning? Not even close. If you had a solar mass of coal, you could power the sun for about 15,000 years at its current brightness. Nothing is going to bring back the coal industry. Gravitational contraction does a little bit better. This is what Lord Kelvin in the 19th century thought powered the sun. That will make the sun go for about 10, 15 million years. But then Marie Curie came along and spoiled the party for everyone by discovering radioactive decay, which allowed us to date rocks on the Earth and know that it was much more than 15 million years old. She also gave us a glimmer of hope. Nuclear fission would get you about 1 billion years, but we know that the sun is not made up of something as heavy as uranium. Fortunately, there is one last hope, and that's nuclear fusion. So hydrogen is the easiest element to cause to undergo nuclear fusion that's out there in any reasonable quantity. But by easy, we mean you have to get it up to millions of degrees. And you take 4 hydrogen, turn them into 1 nucleus of helium. But that nucleus of helium weighs slightly less than 4 individual hydrogen nuclei by about 0.7%. And when you multiply that little difference in mass by c squared with everyone's favorite equation, you get a really substantial amount of energy out. Now, the sun during the main part of its life is going to use about 10% of its hydrogen. So in one line, we can actually figure out what the main part of the sun's lifetime is going to be, just by multiplying the amount of hydrogen available, 10% of 1 times the mass of the sun, times that factor of 0.7% times c squared, that's the amount of energy you have available, and divide that by the rate at which the sun is losing energy. And you end up getting 10 billion years, which is remarkably close to what you get if you do a sophisticated simulation of the sun's lifetime. Now, more massive stars have more gravity to fight against. And they are also far, far brighter, up to millions of times brighter than the sun. And since they are losing energy at this ridiculous rate, they use their fuel faster. And the most massive stars have lives that are only a few million years long. And one way or another, whether it's 3 million years or 10 billion years, you're going to run out of hydrogen, and you have to deal with that problem. When you run out of fuel, nuclear fusion stops and gravity starts to compress the star again. And that heats the interior until you get to the point where heavier elements can fuse. And each stage, as you go to successively heavier elements, is shorter. So we start out with something like the sun going from hydrogen to helium. And then if you look at Arcturus in Taurus, that is a red giant that is turning helium into carbon and oxygen in the core. You run out of helium, and the next thing that would happen is turning carbon into mostly neon, but some magnesium and sodium and other things. But the sun is never going to do that. It does not ever get hot enough in its core. In fact, anything less than about 8 times the mass of the sun never gets to that point. But if you have something bigger like Betelgeuse, you can burn carbon. And that red supergiant Betelgeuse, which is so big that you can actually take an image of its disk from Earth, so about the size of Jupiter's orbit across, is most likely burning helium in its core, but it is an outside possibility that it's in one of its later stages. After carbon, you turn oxygen into mainly silicon and sulfur, but you also get some aluminum and phosphorus and other things. And these stages happen so fast that you actually can't see their effect on the surface of the star. It takes more time for the heat to change the structure of the star than it does, out at 1 billion kilometers, than it does to use up all of that fuel. So carbon burning takes 1,000 years, oxygen burning takes less than a year. So you have to simulate it. And in here, we're looking at the dynamics of the inside of a star as silicon burns down near the core and oxygen burns in a shell a little further out and causes this material to convect and mix and circulate and slosh around in the interior of the star. And then silicon makes calcium and titanium, a little bit of potassium, and successively heavier stuff until it gets to iron. And then iron causes you a problem. Because iron is the most stable nucleus that there is. You end up with this supergiant star, and down in the center, layers of different elements getting heavier and heavier until you get to the center, and that center is not generating energy. Because in order to stick anything to a nucleus of iron, you have to spend energy. It costs you energy to break up that nucleus. And there are a lot of things that are removing energy from this core of the star incredibly quickly. So gravity is finally going to win for the last time. And the star is going to start collapsing from the inside out. Just like poor Coyote's feet realize he's falling before his head, the inner parts of the star start collapsing in before the outside knows about it. And you end up compressing that material down until the inner solar mass and a half is as dense as an atomic nucleus. So dense that protons and electrons combine to form a ball of almost pure neutrons. And what we're going to see in this simulation here is that process of collapse. So at the beginning, things collapse down and we generate our little protoneutron star in the core. And the rest of the star is realizing that it's having a very bad day and falling in on top of that. And it hits that protoneutron star and bounces back outwards. and you have a shock moving out through the star. I'm going to let this run once through, and you'll see that shock moves out and then stops for a while. About there. And at this point, that shock wave moving outward is running into all that material that's falling in, and it just doesn't have enough energy to push further out. So at this point, the event is not going to be terribly spectacular. But this is where those little neutrinos that we mentioned from supernova 1987A come in. They don't like to interact with matter. But down near this proto-neutron star, you are packing about 10 billion grams of material into every cubic centimeter. And that is dense enough to catch 1 in every 100 neutrinos. And those neutrinos heat up this material, and that causes the material to convect like the hot water in a boiling pot. And that material that is heated up and flowing outward carries energy to where that shock was before circulating back down. And that reheats the shock and allows it to overcome that pressure of infalling material, and you get your supernova. And now we're going to zoom out a few times, starting out within the star, and watch that shock move outward. And here you notice something really interesting happen. That shock hit a change in the composition and density of the star and became unstable, making all of these structures little bullets and knobs with high density. And those are going to be very important when we try to get this material with all of these newly synthesized elements out into the universe. You can get all sorts of different shapes of supernova. So these are examples of different simulations that my group has done where you have material moving rapidly out in 2 directions or 1 direction, or circulation going on down in the interior. And some things are common. You always get these knots and fingers that we saw develop in that last movie. And you get these really dense regions down here that are almost like the walls of bubbles around rapidly decaying radioactive material that's heating up the gas inside. And if you take a look at what that material is made out of when you blow up the star, you see that not all of it is the same composition. You're not making a uniform, massive gooey stuff that you're blasting out into the universe. So oxygen will be made in one part of the star and one part of the explosion. Silicon in another. Titanium, iron, all sorts of different things, and they all have different distributions. So if you are shooting material out into the surrounding interstellar gas, different parts of your surrounding are going to get different amounts of certain elements. So I've been showing you a lot of simulations here. How do I know those have anything to do with reality? Well, we can do observational comparisons. So, for example, you can take simulation that we looked at earlier and compare its shape and the kinds of structures that form in it to remnants of supernovae that have exploded in the past few centuries. And you can do a pretty decent job of reproducing that. But even better is when you compare the composition of that material you've blasted out. So this is the Cassiopeia A supernova remnant, that's the one that exploded in 1680. And this is a composite of X-ray, optical, and infrared light. And looking at information like this, you can see where different elements are produced in the explosion. There's some silicon coming out this way. This green blob here is rich in iron. This yellow stuff has a lot of oxygen in it. And if we look in gamma rays, we can actually diagnose the first moments after the explosion. So that process that we looked at of the star collapsing and the shock moving outward and being re-energized takes place over the course of about a second. And we can look at a supernova remnant that's 300 years old, like Cas A, and diagnose what happened in that second. What we're looking at here is information from the New Star Gamma Ray Space Telescope and the XMM Newton X-ray Telescope. These balls with the spikes on them are locations of titanium-44, which is a radioactive form of titanium that has a half-life of about a century. And the little blue orbs are where iron is located in the remnant. And there are two things that pop out at you when you analyze this. The distribution is really asymmetric. There are these blobs. And the other one, when you run the numbers, is when you take a look at the ratio of iron to titanium, it has two specific values depending on where you look. In some places, it's about 500 times more iron than titanium. In the other places, it's several thousand. Now, having these two specific values is not something that simulations have been able to explain. It was quite a surprise when they saw this in the data. So we did some simulations. And what you're looking at here is the orange is density of the material. And the more important part here is the blue and white colors. That is showing the ratio of iron to titanium in our simulation. And it has that same sort of blobby distribution. And it has two distinct values of the ratio between iron and titanium, just like Cas A. And this is important because when you produce elements at temperatures of more than 5 billion Kelvin, the ratio of those two things is really sensitive to the evolution of temperature and density. So we were able to model that convection down near the protoneutron star and blow up the star and make something that looked quite like Cas A. So we were really quite excited about that. And that's exciting to us, but what happened in the interior of one star 300 years ago is a little bit distant from most of us. But that kind of thing plays a huge role in our lives. So let's jump back in time again to 4.6 billion years ago. In a giant molecular cloud where massive young stars were forming, our solar system also formed. While nearby, one of those really rapidly living massive stars finished its life and exploded as a supernova while Earth was still forming. And this brings us to a topic called short-lived radionuclides. So normal aluminum is a happy, helpful element. But it has another version with one less neutron, and that kind of aluminum is radioactive. It has a half-life of only 700,000 years. And there are a number of these isotopes that last about 1,000,000 years or so that we call these short-lived radionuclides. And if we look at meteorites, we find the decay products from this aluminum-26 in calcium aluminum rich inclusions. These are the earliest solid material that formed in our solar system. And the fact that we find the decay products of those species in these early forming little tiny mineral grains tells us that that aluminum-26 had to have been produced and put into the solar system while the solar system was forming. If it had been produced earlier, it would have decayed before finding its way into these little solid grains. If it was produced later, the meteorites would have already formed and it wouldn't have been incorporated. So it had to be some nearby process. And the most likely explanation for that is a supernova. If we take one of those simulations and look at where aluminum-26 is produced in it, and that's what the red stands for in this image, you see these little bullets and fingers are rich in aluminum-26. And those overdense things can slam into a little molecular cloud core or a forming protoplanetary disk and deliver that aluminum-26. And if you blow up a supernova and watch what those little bullets do as they travel out into the interstellar gas, this white material is supernova material. So you can see those bullets, and this simulation is about a light year across. So those structures that you form in the first few seconds and minutes of the explosion can persist out to light years away from the star, which is enough to get them to nearby forming planetary systems in an environment like, say, the Orion molecular cloud. All right, we have this weird, really low abundance isotope of aluminum. Fine, that's interesting, I suppose, but what does it do for us? Well, if you look at how planets form, there is a process called differentiation. So as you slam things together and build up bigger and bigger bodies in the early solar system, that process of accretion releases gravitational potential energy as heat and melts the interior of an object. So you can have metal sink down to form a core, like the iron core of Earth. And then you have a rocky mantle outside of it and a crust. But if you're too small, you don't get this process happening. You just stay mixed up. But put in that extra amount of radioactive heating from that aluminum-26, and you can make much, much smaller things differentiate. So we see one of these objects in the solar system called Psyche, which appears to be a metal asteroid. And this is the bare core of one of these objects that had its crust and mantle stripped off of it by impacts. And it is much too small to have formed just through differentiation from accreting material together into its parent body. It needed that extra heat source of aluminum-26. So the objects in our solar system look significantly different because of that aluminum. It also provides heat that drives off volatile things like water, for example. If you look at Earth, we tend to think of it as a wet place because it has oceans, but that's about 0.15% of the weight of Earth. It's really very dry. And one of the reasons for that might be because it was heated up and the water driven off by this aluminum-26. And you can imagine that if our solar system had not received that when it was forming, it might very well have a planet that's half water in the place of Earth. And we do see extrasolar planetary systems with planets that look quite like that. On a sort of larger scale, you can change the abundances of more common things like, say, magnesium and silicon. And if you change the ratio at which those are present, you make different minerals. So two that are very common in Earth are pyroxene, which has one magnesium for every silicon atom, and olivine, which has two magnesium for every silicon. Earth's mantle is made up of a mixture of these two. But we see stars whose composition tells us that they are likely to have much more magnesium relative to silicon, so you would have planets that are mostly olivine and its high pressure variations down in the deep interior. These different minerals have different physical properties. So if you go to our main building at ASU, if you can ever do that again, you will find labs where my colleagues actually reproduce the conditions down near the boundary of the core and mantle of the Earth and the crust and mantle of the Earth to measure the properties of these minerals. And it turns out that olivine flows 100 times more easily than pyroxene. So if you had a planet that was made out of mostly this high magnesium to silicon kind of mineral, instead of like Earth, half and half, convection in the interior would be very different. The way that you move continents around, the way that you transport heat from the core to the surface could be much more vigorous, and that would change your plate tectonics, your volcanism, what your crust is look like, how fast you are exchanging gases between the atmosphere and the interior of the planet, whether those processes might overwhelm the rate at which gases are being produced by life that you're trying to find signs of. So studying these interiors of stars as they explode tells you about the interiors of planets that you're going to make and their ability to support detectable life. Carl Sagan said that the nitrogen in our DNA, the calcium in our teeth, the iron in our blood, the carbon in our apple pies were made in the interiors of collapsing stars. We are made of star stuff. And if you wish to make an apple pie from scratch, you must first invent the universe. And my corollary to that is, then you must blow a lot of it up. Thank you very much. I am happy to take questions. Good question. So the question in the chat is, how long has the collective info presented tonight been commonly known and understood in the scientific community? There is quite a range. So it's been known that massive stars go supernova since at least the 1960s, with some idea of the mechanism. So part of it, that bit with the shock of material bouncing off that hard neutron star, that was an idea first developed in the 60s and 70s. Figuring out that you need to capture those neutrinos and use them to blow up the star, that's an idea that started in the 80s and 90s. The ability to do those 3D simulations is something that's happened since the turn of the century, and actually following out that development of the structure from the explosion to the supernova remnants and figuring out how that stuff is delivered to the interstellar gas is something that I'm currently working on. And the idea that it affects planetary interiors and behaviors is also something very new. Certainly, we know that minerals have different properties and such, but applying that to the idea of exoplanets, figuring out that they might have very different compositions and therefore behaviors from Earth is also stuff that we've been actively working on in the last few years. So yeah, a lot of the actual simulations and stuff I showed you are current research, but there was some bedrock background underlying it. Yes, I should have mentioned that. A spacecraft is being built for launch in 2022, I believe, and the principal investigator of that project is our very own Lindy Elkins-Tanton. It should arrive there in 2026.
I'm going to speak out here. I saw something on that a while back, and they said it's high in minerals, and they're going to investigate it for possible mining. Is that what?
Yeah,
true?
so since it's the bare metal core of one of these small bodies, it is made up largely of iron and nickel and smaller proportions of other metals. It's got a little bit of rock on the surface, not much. The mission that's also called Psyche is purely scientific. It's going there to figure out what's going on because we've never observed an object like this up close. But it's not going to do anything related to mining itself. However, there are tons of proposals out there dating back to the 1930s about mining asteroids, since ones like this are huge lumps of metal that are easy to get to once you've taken the step of getting into space.
I see there's another question here from Bruce.
Yes, did the olivine on the beach in Hawaii come up from the interior magma rather than from the ocean? Yeah, so the Hawaiian Islands sit on top of what is called a hotspot plume. So that's actually hot material that's moving up from fairly deep in the mantle and breaching the crust and exuding onto the surface. And that's why you have a chain of islands, because the tectonic plate of the Pacific is moving over that hotspot. And as it moves, the volcanism makes a new island every once in a while along that line. So olivine is actually a really common thing to get in magma from volcanoes. So the mid-ocean ridges, volcanoes like Hawaii, shield volcanoes are mostly olivine. It's a very common mineral.
Does anybody else have any more questions? This is fascinating, absolutely fascinating. And I want to concur to Bruce's thing. Thank you very much. What a great presentation. There, just all the stuff about the stars, you know, it is amazing. So, anybody have any other questions for Patrick? Nope, that's about it, I guess.
All right, in
All right,
that
well,
case, thank you very much for having me. Thank you very much for putting up with the technical difficulties. It would be great to meet you all in person someday.
Well, let's see, you're just down at ASU, so maybe we will cross paths. You know, we can finally get back to meet again as a group.